Hi, welcome to gravitational fields. So gravitational field strength G at a point is defined as a gravitational force per unit mass acting at a point. We've done that before, okay, so it's simply just how the definition is worded. So the formula will be G equals force per mass. Now what's the unit? Well, it's just newtons per kg. Okay, so it's saying for every sort of object, okay, it's going to have a force for every unit of mass in that object. So if there was 10 kgs, well, that's going to be 100 newtons, okay. Now, how do we represent, well, what is actually a gravitational field? Well, a field itself, the lines represent a force field, okay, and if you put a certain object in there, in this case for gravity, if you put in a mass, that mass will feel a force. Now the direction of the field lines in this case show the direction the force would feel a force. So what can we represent? Well, the direction is given by the direction the mass would feel a force. So mass, force, direction. Okay, and the strength of the field is given by the spacing. Okay, and if you look at the Earth here, where's the greatest strength? Right in there. Okay, something that's very important is that all fields from the surface must leave at 90 degrees. Okay, so not like that one, they should all be at 90 degrees. Now, usually when we look at what we've done in year 12, 11, 10, 9, and so on, we're taking G as being constant. For example, if you use this formula here, that is telling us that we're using G constant over a certain h, okay, height, which is actually not always true, because as you leave the Earth, if you go outwards, the G will actually reduce. So just a quick example, consider 4 kg mass and a gravitational field strength of 5 newtons per kg. Okay, what's the weight of it? Well, that's the force. So force equals, this is from your formula, G equals F over m. So force equals gravity times mass. So it's going to be 5 times 4, which equals 20 newtons. What's the acceleration? Well, then you've got F equals ma, so A equals F over m. So you're going to do 20 divided by 4, which equals 5 meters per second per second. And that's where you can see the relationship between gravitational acceleration and the strength of the gravitational field. Okay, what we're going to get really into is the Newton's law of gravitation. Okay, essentially Newton said that gravitation is a force between two things that have mass. Okay, now it's actually the size of it is proportional to the product of the two. So we multiply these two together, the product of the two masses, but it's inversely proportional to the square of the distance away. So the distance between these two is r. Okay, and if you, let's say, you double the distance away, so we multiply that by 2, then your force is going to go down by 4. Okay, so the force of attraction is proportional to mass 1 times mass 2, and it's also proportional to 1 over r squared. Now whenever you have some sort of formula that is y is proportional to x, to make it into an equals, we put in a constant, okay, like that constant gradient m. And in here, this is what he said. Okay, you can read that. Essentially, it's just what I said. So this is going to add in some constants, okay, so and so on. So we're going to make it F equals G, big M, little m, over r squared. Okay. Some textbooks will show you that as a negative. but we're not that concerned. Okay, so remember this comes from the, you could actually label those, that's a force proportional to the product of the two masses and inversely proportional to the square of the distance between them. G, the constant, is very small, okay? It's a very small constant. What's the unit? Well, Newton, meter, kg, and there's a -2 going in there somewhere, okay? So what we're going to do to make sure, one important thing is that when we measure the distance, it's always between the center of the two masses, okay? And usually we're talking about gravitation, so the actual radius of the masses usually doesn't matter, so we take it from the centers of each, because they're usually quite small in comparison to the distance between them. So doing an example, you can just chuck it in, F equals G M divided by R squared, 6.67 times 10 to the negative 11 times 70 times 60, divide all that by 0.75 squared, and you'll find some small number. Okay, so the force of attraction between two masses that size, very small, but if you've got something like the Earth, which has a mass of 6 times 10 to the 24 kgs, okay, I think it's that, then that is very large. Okay, it's because of this term here. It makes things small.